This is Bill Vining, and we are going to do 23 net ionic equation examples. No more, no less. We're going to be using our data tables, our solubility chart for solubility of ionic compounds, our listing of strong acids and bases, as well as our listing of weak acids and their weak conjugate bases, as well as the three main kinds of gas-forming reactions that happen when acids are added to carbonates, sulfides, and sulfates. Okay, first example, zinc iodide and lead nitrate. So we'll write out our two reactants. Zinc iodide, that is soluble in water because iodides are generally soluble in water. Lead nitrate is soluble in water because all nitrates are soluble in water. Then what we do is we swap the two ions to do our double displacement reaction. So zinc will end up with nitrate, lead ends up with iodide. Zinc's 2+, so it will have two nitrates when it gets formed. So zinc nitrate, we'll have that formula, that's aqueous. And then lead will end up with the iodide, so that's PbI2 because the lead's 2+, and the iodide ions are -1. And now we're going to look at our solubility chart. So the solubility chart says that iodide salts are generally soluble, but lead is an exception to that. So lead iodide is a solid. And that's our precipitate. So it's a precipitation reaction. So we write out zinc 2+ plus 2, I had a 2 there, 2I- plus lead 2+ plus nitrate minus 2 nitrates goes to make zinc 2+. We're writing out our full ionic equation now, plus 2 nitrates plus PbI2. Now, because the PbI2 is a solid, it stays together, and all of these other ones are aqueous. I'm going to spend a lot of time this morning writing aqueous signs. I tell you that right now. Right now, I tell you. Okay, so now we look for spectator ions. The zinc is in solution to begin with. It's in solution to end, so the zinc is a spectator ion. The iodide's in solution to start with, but it ends up in a solid, so that's not a spectator ion. The lead starts in solution, it ends up in a solid, so it's not a spectator ion, but nitrates are in solution both times. So they are spectator ions. So our net ionic equation is PbI2 aqueous plus 2I- aqueous goes to make PbI2 solid. Now notice that iodide salt could have been just about any iodide salt that starts out soluble. Sodium iodide, could have been iron 2 iodide, could have been calcium iodide, and the net ionic equation would have been the same. Okay, next experiment. Iron 3 iodide with sodium hydroxide. Now notice sodium hydroxide is a base, and so you have to think about whether or not this will be an acid-base reaction, but there's no acid. Iron iodide is not an acid, so it's not an acid-base reaction, but it might be a precipitation reaction. So let's go ahead and write it out. Iron 3 iodide is going to be FeI3. That's soluble, so that's aqueous. So while I'm doing this, this time I'm going to do it in a slightly different order. I'm going to write out my net ionic, my full ionic species as we go along. So iron iodide, iron 3 iodide is iron 3+, 3 iodides, aqueous. Sodium hydroxide, I just realized that's a bad idea. We're not going to do that. That is aqueous because sodium hydroxide is soluble. That's aqueous. Those are going to react. The iron is going to end up with the hydroxide. The sodium is going to end up with the iodide. So we make sodium iodide. That is a soluble salt because sodium salts are soluble. Iodide salts are normally soluble. We're going to make iron 3 hydroxide. So it's FeOH3. Remember, the OH goes in parentheses, the whole OH. And that is to swap. Okay, I need my keyboard back. Alright. So Hydroxide salts are generally insoluble. Iron is not an exception to that. So iron 3 hydroxide is a precipitate. It's solid. Okay. So then we have to balance that. Because we have 3 hydroxides, we're going to need 3 sodium hydroxides. And now we have 3 iodides and 3 sodiums. So we're going to have 3 sodium iodides. So our 3 sodium hydroxides are going to be 3 Na plus aqueous plus 3 hydroxides aqueous. Those go to make 3 sodium iodides, so that's going to be 3 sodium plus aqueous plus 3 iodide aqueous plus the iron hydroxide solid. Okay, so spectator ions or iodides are on both sides the same. Sodium's on both sides the same. So our net ionic equation is iron 3 plus aqueous plus 3 hydroxides aqueous go to make iron 3 hydroxide solid. Okay, so that reaction is a precipitation reaction. Okay, example number 3. Iron 2 sulfate plus lead 2 acetate. So iron 2 sulfate. Sulfate's a 2- salt, so it's going to be 1-to-1 with iron 2 plus. FeSO3, that's going to be aqueous. Plus lead acetate, that's Pb. Acetate is CH3CO2. That's a 1- ion, so that's 2 of those. Acetate salts are always soluble, so that's aqueous. That's going to go to make lead sulfate when we swap the ions. So iron goes with the acetate. Lead goes with the sulfate. Lead sulfate's insoluble. I'll show you why that is in a second. And iron 2 acetate will be an iron 2 plus ion and 2 acetates, and that will be soluble because acetate salts are soluble. Sulfate salts are generally soluble, but lead's an exception to that. So lead sulfate is a solid, so it's precipitate. So we start out with iron 2 plus. This breaks up into ions, so it's iron 2 plus aqueous plus sulfate 2- aqueous plus lead 2 plus aqueous. You know it's 2 plus because it tells you, but also because there are 2 acetates at this stage. Plus 2 acetates. Acetate will always be aqueous because it's always soluble. That goes to make lead sulfate solid plus iron 2 plus aqueous plus 2 acetates aqueous. Okay, and so now the iron 2 plus is a spectator ion, the acetates are a spectator ion, and what we have is we have the sulfate 2- aqueous reacts with the lead 2 plus aqueous, goes to make the lead sulfate solid. It's another precipitation reaction. Okay, potassium phosphate and nickel bromide. So potassium phosphate is going to be K3PO4 aqueous. Nickel 2 bromide is going to be NiBr2. That's aqueous. That's going to go to make, if we swap the ions, it's going to make potassium bromide. That's going to be aqueous. And nickel phosphate. So nickel phosphate, nickel's 2 plus, and the phosphate's 3-. So we're going to need 3 nickels and 2 phosphates. And phosphate salts are generally insoluble. Nickel's not an exception to that. So nickel phosphate's going to be a solid. So that's our precipitate. Okay, we need to balance this. We're going to need 2 phosphates. We'll put a 2 there. We need 3 nickels, so we'll put a 3 here. And now we've got 6 potassiums and 6 bromides, so we'll put a 6 there. Okay, so we now have 6K plus 2 phosphates plus 3 nickel 2 plus 2 Br minus. Those go to make 6 Br minus, because you have 2 of them in each nickel bromide, but there are 3 nickel bromides. 6K plus that's aqueous, plus 6Br minus, that's aqueous, plus the nickel 2 phosphate, which is a solid. And so all of these are aqueous as well. So our spectator ions are going to be the things that don't change, and those are going to be the potassium ions and the bromide ions. And so our net ionic equation is 2 phosphates plus 3 nickel 2 pluses goes to make nickel phosphate as our solid precipitate. All right, next. Hypochlorous acid and barium hydroxide. Hypochloric acid is HClO, and that is soluble because all acids are soluble. The other thing to remember, that's a weak acid, so it's going to start out and not split up into ions. Barium hydroxide is BaOH2. That is, I'm going to go back for a second, that is soluble. And so hydroxide salts are generally insoluble, but barium is an exception to that. So that's soluble. So that's aqueous. Now, barium hydroxide is a base. Hypochlorous acid is an acid. So these hydrogens are going to end up with the hydroxides to make waters. And the hypochlorite ion is going to end up with the barium. So we're going to make barium hypochlorite. It's a 2-to-1 because that's hypochlorite's a -1 ion, and that's going to be aqueous. Then I'm going to make 2 waters from the 2 hydroxides with the hydrogens there. And so that's liquid, because water is a liquid in a liquid state, because it's dissolved in water, but you can't have water dissolved in water. And to balance this, you're going to need a 2 here. So what happens then is that the net ionic equation, the HClO, the overall ionic equation, starts out together because it's a weak acid. It's soluble because it's an acid. It's written together because it doesn't split up automatically in solution. Barium hydroxide is a soluble salt, so it exists as barium 2 plus 2 hydroxides. Both of those aqueous. And then barium hypochlorite is going to be Ba2 plus aqueous, plus 2 hypochlorites aqueous, plus 2 waters. Oh, sorry, 2 of these here. Okay, now the spectator ions, there's only one here, it's barium. Barium's the only spectator ion. So the spectator ion is 2 hypochlorous acids. Those are aqueous. Those react with 2 hydroxides. Those are aqueous. And that goes to make 2 hypochlorite ions plus 2 waters, liquid. So again, this is an example where it doesn't really much matter. Any soluble hydroxide salt would have given us the same net ionic equation in the end. So if you had potassium hydroxide or sodium hydroxide, it all would have been the same. Okay, potassium hydroxide and hydrosulfuric acid, which is H2S, and that's aqueous, dissolved. So potassium hydroxide is KOH. That's obviously a strong base. H2S is a weak acid. We can see it on our acid sheet here. The product, when that acts as an acid, is the thing found on the other side. It'll be S2 minus sulfide ion. And so what's going to happen is each of the hydrogens here is going to be lost. It's going to lose 2 hydrogens, and those hydrogens are going to react with the OH to make water. So we're going to have to make 2 waters because you have 2 acidic hydrogens. So we're going to need 2 of those. One of these will make 2 waters, and the potassium is going to end up with the sulfide, so it's going to make K2S. Now let's go back for a second. H2S is going to be soluble because it's an acid, but it's going to stay together because it's a weak acid. Our potassium sulfide we have, sulfides are generally insoluble, potassium's an exception to that, so that is soluble. Again, you can also say potassium salts are always soluble. So that's soluble. So now when we write things out, the potassium hydroxide soluble, because it's a potassium salt, we're going to have 2K plus aqueous plus 2 hydroxides aqueous plus H2S, that's aqueous. Remember, it's soluble because it's an acid, but it stays together because it's a weak acid. It's going to make 2 waters. Those waters will be in the liquid state, as waters always are in water. And the potassium sulfide is soluble. It's a soluble salt, so it's split up. So it's 2K plus aqueous plus sulfide aqueous. All right, so let's see what we got here. So we have the potassiums are the spectator ions, and the rest are not. So we have 2 OH minus plus H2S plus 2 waters plus sulfide ion. So basically what happens in this reaction is the hydroxide ions come and steal the H pluses off the sulfide ion. So you've got 2 hydroxides, they grab those 2 H pluses, and the H pluses end up on water, and the sulfide ends up losing its hydrogens. He's sniffling now. Calcium carbonate and hydrochloric acid. So calcium carbonate is CaCO3. Calcium's 2 plus, carbonate's 2 minus. So they're 1 to 1. That is insoluble because carbonate salts are generally insoluble, and calcium is not an exception to that. Hydrochloric acid is HCl, of course. That is aqueous, and that's going to break up when we get to it. Now, this is one of the reactions that's a gas-forming reaction. When you have carbonates, which are weak bases, react with acids, what happens is those go to make, at first they make H2CO3, but that H2CO3 breaks up into water and carbon dioxide. So each carbonate is going to make water and carbon dioxide, but it needs 2 hydrogens to do that. And so we're going to need 2 HCl's. And what we're going to make is the calcium's going to go with the chlorides. So we're going to make calcium chloride. That'll be aqueous. But then instead of making H2CO3, we're going to make water as a liquid and CO2 as a gas. So you need to remember that the gas-forming species are carbonate, sulfide, and sulfate. Okay, so our full ionic equation will be calcium carbonate's written together because it is together, because it's a solid. The HCl is soluble because it's an acid. Because it's a strong acid, it starts out split up. That's what a strong acid is. It's an acid that is already split up into ions before the reaction occurs. That goes with calcium carbonate. The calcium will be in solution, as will the separate 2 chloride ions. They'll be in solution as well. Plus a water, which is a liquid, plus carbon dioxide, which is a gas. Okay, the only spectator ions are the chlorides. So we have calcium carbonate as a solid, plus 2 H pluses. That's aqueous. Goes to make calcium 2 plus. It's been a while since that happened, so I got a little spike there. Calcium 2 plus, that's aqueous. Plus water, plus carbon dioxide. So this is a method for dissolving calcium carbonate. It's insoluble. When you add acid to it, it actually dissolves, and the calcium ions are free, and the carbonate is largely gone because it turned into CO2. Okay, potassium sulfide and hydroiodic acid. Potassium sulfide is K2S. It's soluble because potassium salts are soluble. Hydroiodic acid is HI. And what happens is, when we look at our acid-base chart, sulfide ion, when it reacts with an acid, it makes H2S. But remember, that's a gas-forming reaction, so our H2S is going to be a gas as opposed to being aqueous. So because we've got an S2 minus, and we're going to make H2S, we're going to need 2 hydrogens. So we're going to need 2 HIs. Those are aqueous. That's going to go to make H2S, as we just mentioned. And that is going to be in the gas phase instead of aqueous. and it's going to make 2 KIs, which will be aqueous. Now, remember that HI is one of the strong acids, so it is broken up into ions. So it's going to be 2H plus aqueous plus 2I minus aqueous. And the potassium sulfide is a soluble salt, so it's 2K plus aqueous plus S2 minus aqueous. Because all soluble salts are broken up. That goes to make H2S gas plus 2K plus 2I minus aqueous and aqueous. So the K plus is a spectator ion, and the iodides are spectator ions. So here we just have S2 minus aqueous plus 2H plus aqueous going to make H2S. And that's a gas. So in this case, this could have been any soluble sulfide salt. It could have been sodium sulfide, it could be ammonium sulfide, and this could have been any strong acid. It could have been nitric acid or HCl, and you would have ended up with the same net ionic equation. Hydrochloric acid and calcium sulfite. Hydrochloric acid obviously is HCl. It's a strong acid, as you know, so it's soluble. That's going to be calcium sulfite, which is CaSO3. And it's telling us that that's a solid because you wouldn't have known because there's no rule for sulfites. So that's a solid. Sulfite, remember, is one of the gas-forming reactions. So when it reacts with an acid, it's going to react with 2 H pluses. It's going to make water and SO2 gas, very much like the carbonate reaction. So we're going to need 2 hydrochloric acids because 2 of the 2 hydrogens need to react with the SO3. So that's going to make water. That'll be a liquid, plus SO2, that's a gas, plus calciums go with the chlorides, CaCl2, aqueous. Okay, to start out, the HCl is a strong acid, so it's 2H plus aqueous, plus 2Cl minus aqueous, plus the calcium sulfite is solid, which it tells us. And that's going to make a water, which will be liquid, and SO2, which will be gas, and calcium chloride, which will be aqueous. What am I doing? What am I doing? That calcium chloride is a soluble salt. So that's calcium 2 plus aqueous, plus 2 chlorides, aqueous. All right, so what has not changed? The only thing that hasn't changed is the chlorides. Everything else has changed. So our net ionic equation is 2H plus aqueous plus calcium sulfite solid goes to make water, liquid plus SO2 gas plus calcium 2 plus. And so this is another example where you could have used any strong acid and the net ionic equation would have been the same. Okay. Hey, wait, that's the same one. Skipping that one. Okay. Chromium 3 sulfate and potassium hydroxide. So chromium 3 sulfate, chromium is going to be 3 plus, sulfate's 2 minus. So we're going to need 2 chromiums and 3 sulfates for that compound. And that's soluble because sulfate salts are soluble. So why am I writing solid? Because I'm wrong. That's aqueous. That's going to react with potassium hydroxide, KOH. The OH is going to go, the KOH is a base, there's no acid here, so it might be a precipitation reaction. We'll find out. The potassium is going to go with the sulfates, and the hydroxides are going to go with the chromium. The chromium is a 3 plus. The hydroxides are 1 minus, so it's going to be CrOH3. And that's going to be a solid because hydroxide salts are generally insoluble, and chromium is not an exception to that. And then we're going to make potassium sulfate, K2SO4, because sulfate's 2 minus, potassium is 1 plus. Potassium sulfate will be soluble because it's a sulfate salt. That's potassium salt. And we got to balance this now. We need 2 chromiums on the left. We need 2 chromiums on the right. We now need 6 hydroxide. So it looks like we're going to need 6 KOHs. And we're going to need 3 sulfates. So we're going to need 3 potassium. So I think that's all balanced. Okay, so we're going to have 2 chromium 3 pluses, aqueous, plus 3 sulfates, aqueous, from the chromium sulfate, which is soluble, plus 6 potassiums, 6 potassium hydroxide, so it's 6 potassium ions, plus 6 hydroxide ions. I'm going to run out of room. Goes to make 2 CrOH3. That's written together because it's a solid. Plus 3 potassiums and 6 potassiums, because there's 3 of those which have 2 H. 6 potassiums and 3 sulfates. So that's aqueous. That's aqueous. Yeah. So the spectator ions will be the sulfates and the potassiums. So our net ion equation is 2Cr3 plus aqueous plus 6 hydroxides aqueous goes to make 2 CrOH3 solid. Now, this is an example like regular balancing reactions where you have stoichiometric coefficients that are all, that can all be cut in half. And so we have to cut that in half. So the real reaction then is Cr3 plus aqueous. You have to get the smallest integers you can, plus 3 hydroxides aqueous goes to make CrOH3 solid. So when you balance equations, sometimes you end up with coefficients that are double what they need to be, or triple what they need to be, and then you condense it down to the smallest integers. Okay, nitric acid and aluminum phosphate. So nitric acid is obviously a strong acid, so that's HNO3, that's aqueous. Aluminum phosphate is, aluminum 3 plus, phosphate is 3 minus, so they're 1 to 1. Aluminum phosphate will be solid because phosphates are insoluble. Now, if we look at our data chart, phosphates are insoluble, so that's why that's a solid. Phosphate is a weak base, and when it reacts with an acid, it makes H3PO4, phosphoric acid, which will be soluble but written together because it's a weak acid. So we're going to make H3PO4. Some of the hydrogens are reacting with the phosphate, the aluminum's reacting with the nitrate. That's going to be aqueous. And then the aluminum is going to be paired with the nitrates. Aluminum is 3 plus, nitrate is 1 minus, so you're going to need 3 nitrates. Nitrate salts are all soluble, so that's aqueous. And then to balance, we're going to need 3 nitric acids. So that's written out then as 3H plus 3 NO3s, 3 minuses, plus aluminum phosphate, that's a solid. These two are aqueous. That goes to make phosphoric acid. That's written together because it's a weak acid, but it's aqueous because all acids are soluble. And aluminum nitrate is a soluble salt, so that's going to be separate ions in solution. Aluminum 3 plus aqueous, plus 3 nitrates aqueous. So nitrates are changing, and that's it. So our net ionic equation is 3H pluses aqueous plus aluminum phosphate solid goes to make H3PO4 aqueous plus aluminum 3 plus. So this is an example of a reaction that would dissolve aluminum phosphate, which is insoluble, because the strong acid goes and adds its hydrogens to the phosphate, which then dissolves and setting the aluminum free. Hydrochloric acid and silver nitrate Hydrochloric acid is an acid. You see, is there a base for it to react with? And there isn't. Silver nitrate is not a base. So it might be a precipitation reaction. So it's HCl, aqueous. Silver nitrate is HNO3. That'll be aqueous because nitrate salts are always soluble. When you react then, the hydrogen ends up with the nitrate and the silver ends up with the chloride. So you make silver chloride. Now, chloride salts are generally insoluble, but if you look at our chlorides here, chloride salts are generally soluble, but silver is an exception to that. So you make silver chloride, which is a solid. Plus, you make nitric acid, HNO3. Aqueous. HCl is a strong acid, so it's written up separately. H plus Cl minus, both of those aqueous. The reaction was 1-to-1, so we didn't have to do anything else to balance it. Plus silver nitrate is soluble, so it's written out separately. So you have all 4 separate ions. The silver chloride you make is a solid, so it's written together because it's solid. It is, in fact, together. The nitric acid is a strong acid, so that's written out together. I mean, written out separately. So the hydrogen ions are spectator ions. The nitrate ions are spectator ions. We end up with silver plus. You can write it in either order. The chloride could go first. I generally write the metals first because they're going to be first in the product, but it doesn't really matter. It matters when you write the AgCl, the Ag has to be first. The metal has to be first. Cations are always first in ionic compound formulas. Okay, so that one there, that's the precipitation reaction. Hydrochloric acid and sodium acetate. Hydrochloric acid is HCl. That's aqueous. Sodium acetate is NaCH3CO2. That's aqueous. Hydrogen goes with acetate, so it makes acetic acid. Look at our data chart. Acetate is a weak base. When it reacts with hydrogen from an acid, it makes acetic acid. So you can write acetate either COO or CO2. So that makes that. That is going to be aqueous because all acids are aqueous. Plus, the sodium goes with chloride, so it makes sodium chloride. That's aqueous. All right, so the HCl is a strong acid, so it's written out separately. H plus Cl minus, aqueous, plus sodium acetate. That's a soluble salt, so it's sodium plus an acetate ion, which is they're both separate because it's a soluble salt. Then we have our acetic acid, which is written out together because it's written together because it's a weak acid, but it's soluble because it's an acid. All acids are soluble. It's a weak acid, so it's together. It doesn't split up in solution. And that leaves us with sodium plus aqueous and chloride aqueous. So sodium plus and chloride will cancel, and our reaction is an H plus from the strong acid protonates, as we say, the acetate ion, the weak base, to make acetic acid. All right, sulfuric acid and ammonia. Sulfuric acid is H2SO3, and that's a strong acid. It's a strong diprotic acid, so it's going to lose both hydrogens. So that's aqueous because it's an acid. Ammonia, as you know, is NH3. Ammonia is a base. It's going to accept a hydrogen because there are 2 hydrogens in sulfuric acid. We know already we're going to need a 2 there. So that's aqueous because ammonia is soluble. And our products are going to be the hydrogens are going to go in the NH3, so we're going to make NH4 plus, and that's going to be aqueous. And we're going to make 2 of those because we have 2 hydrogens here and 2 ammonias, and we're going to be left with sulfate ion, which is aqueous. So our sulfuric acid starts as 2H plus aqueous, plus a sulfate, aqueous, plus 2 ammonias, aqueous, goes to make 2 ammonium ions, those are aqueous, plus sulfate ion aqueous. So the sulfate ion is the spectator ion. The only thing that's happening here is the sulfuric acid has already given up its H pluses, and the H pluses are just reacting with the ammonia to make ammonium. So we're going to have two H pluses plus two ammonias plus going to make two ammonium ions. So we're going to split that in half. And the final equation is going to be H plus plus NH3. Both of those aqueous go to make ammonium ion aqueous. And that's another example where that reaction will be the same regardless of what strong acid you used. Sulfuric acid and potassium hydroxide. Sulfuric acid is H2SO4 plus KOH. A strong acid and a strong base goes to make water and potassium sulfate. So potassium sulfate is aqueous, the water is liquid, the KOH is aqueous, and sulfuric acid is aqueous. Now we talked about how all reactions between a strong acid and a strong base all have the same net ionic equation of H plus OH minus goes to make water. And we don't generally want to just memorize things, but that's just worth memorizing. Strong acid, strong base goes ahead and does that. And let's go ahead and work it through to show that that's true. 2 H pluses plus sulfate plus 2, balance it. I need a 2 there to balance it. And there's 2 waters to balance it. 2K plus 2 OH minus goes to make water in the liquid state, plus 2K plus sulfate. These are all aqueous. Aqueous. I brought the worst aqueous signs. So the hydrogens end up with the hydroxides to make water. So those are not spectator ions, but the sulfates and the potassiums are. So you end up with 2H plus 2H minus goes to make 2 waters. Just split that in half, and then you have your standard net ionic equation for strong acid and strong base. Okay, calcium hydroxide and ammonia. Calcium hydroxide is CaOH2, and that'll be a solid. Ammonia is NH3, and that'll be aqueous. Now, ammonia is a base, and calcium hydroxide is also a base. So they don't have any reaction. There's nothing to happen there. You can't make a precipitate out of ammonia, and ammonia can only act as, the only thing it can act with is an acid. There's no acid, so nothing happens. Potassium acetate and sodium bromide, that's going to be KCH3CO2, that's aqueous, plus sodium bromide is NaBr, that's aqueous. That's going to go to make potassium bromide. Potassium goes with the bromide, sodium goes with the acetate, plus sodium acetate. Aqueous. Okay, so we've got K plus CH3 CO2 minus plus Na plus Br minus. And I'm just going to collectively say all of those are aqueous. And that makes KBr, that's soluble, so that's split up into ions, K plus Br minus. And sodium acetate is also soluble, so that makes Na plus CH3CO2 minus. And all of those are aqueous. And so everything cancels. And so therefore, there's no reaction. You have a bunch of ions in solution. When you mix two solutions together, they're still in solution. They haven't done anything. So there's no reaction for that. Everything cancels. Ion 2 carbonate and hydrobromic acid. So whenever you have a carbonate and an acid, you're going to have a reaction that makes carbon dioxide and water based on this reaction here. So the only thing we have to do here is make sure we have the right formulas for things. So iron 2 plus and carbonate 2 minus go together 1-to-1 to make iron carbonate. We know the carbonate is going to need to react with 2 acids, so we're going to use 2 hydrobromic acids, 2 HBRs. Those are aqueous. That's going to make iron bromide, iron 2 bromide, which would be FeBr2, and that'll be aqueous because it's a bromide salt. And then the hydrogens are going to react with the carbonate, and remember that's a gas forming reaction, so the H2, the two H pluses and the carbonate go to make water and CO2. So that goes to make water as a liquid and CO2 gas. All right, so when we break this up, we're going to have iron, when we do our full ion equation, the iron carbonate is written together because it's a solid. The HBr is aqueous because it's an acid. It's broken up to start with. It's fully ionized to start with because it's a strong acid. So it's 2 H pluses and 2 Br minuses. The iron 2 bromide is a soluble salt, so it's going to make iron 2 plus aqueous plus 2 bromides aqueous. That's split up. The water is going to be water as in the liquid state, and the CO2 is going to be a gas. So the only thing that's a spectator ion here is bromide ion. And so we have FeCO3 solid plus 2 H pluses goes to make iron 2 plus aqueous plus water in the liquid state plus CO2 gas. All right. Now, this is our last example. Lead 2 phosphate and nitric acid. So lead 2 phosphate, lead has a 2 plus charge. So lead 2 phosphate is going to have 3 leads, 2 phosphates. That's going to be insoluble because phosphates are insoluble. That's going to react with nitric acid, HNO3. That's soluble because all acids are soluble. The hydrogens are going to go on to the phosphates. And remember what happens here is if you have phosphate ion, if you react it with an acid, it's going to make H3PO4. We saw that in an earlier example. So it's going to make H3PO4, and that's going to be aqueous. Plus, the lead is going to end up with the nitrate, and lead's 2 plus, and so it gets 2 nitrates. Because nitrates are 1 minus each, and that's aqueous because nitrates are always soluble. So we have 3 leads, so we're going to need 3 lead nitrates. We have 2 phosphates, so we're going to need 2 phosphoric acids, so therefore we're going to need 6 nitric acids. So Pb3, PO4, 2 solid, plus 6 H plus 6 NO3 minus. That's broken up because nitric acid's a strong acid. It's soluble because it's an acid. That goes to make 2 H3PO4s. That is written together because it's a weak acid. Weak acids exist in solution without giving up their hydrogens. That leaves us with 3 lead ions. Those are 2 plus each, plus 6 nitrate ions. Okay, so the nitrates cancel, and the rest does not. So our net ionic equation is Pb3, 2 PO4s, that's a solid, plus 6 H pluses, that's aqueous. That goes to make 2 phosphoric acids. Those are aqueous. And the lead ion. So there's a reaction that will dissolve lead phosphate by essentially stealing the phosphates off the lead phosphate using the acid. All right, that is it. That is our many net ionic equation examples. And I hope you enjoyed them as much as I did.